Hi students, welcome to our next lecture. We continue talking about NP completeness. Possibly the last time, possibly a little bit more next time. So we talked, what did we talk about? We talked about 3-SAT being our kind of fundamental NP complete problem, and then a whole bunch of other problems can be proved to be NP complete by reducing 3-SAT to them, right? So if we learned to quickly solve those problems, then you will be able to quickly solve 3-SAT, and therefore they are NP hard, and then you check they are also in NP, and you know they are NP complete. So of course, you don't have to reduce 3-SAT to everything. Once you know that something is NP complete, you can reduce it to something else, and that something else will be NP complete too. So, but it sometimes turns out to be just frequently convenient to reduce specifically 3-SAT to different problems. So in the homework, you'll have examples when it's more convenient to reduce something else to whatever you want. Okay, so let me remind you what was 3-SAT. 3-SAT was the problem of satisfiability of something like x1 or x2 or x3 and y1 or y2 or y3 and something like this, right? So this is conjunctive number form, more specifically. So which means that there are parentheses, inside parentheses you have ors, outside ends, and it's 3-SAT because we assume each parenthesis has exactly 3 things. And deciding whether such formula is satisfiable means that just if there is assignment of true or false, or 1 or 0 to each variable, which makes it true, is a NP complete problem. So you could ask, what about 2-SAT? What if we had a simpler formula, something like this, x1 or x2, and y1 or y2, and etc. Is this NP complete? It turns out, so if it was, then of course we should use this one because this one is simpler. But it turns out that it's not NP complete. In fact, is in P. All right, so there is a polynomial time algorithm to decide whether 2-CNF formula has, or 2-SAT formula has satisfying assignment. So let's see what it is. So let's see what this polynomial time algorithm is. So let's say we have 2-CNF formula. For example, I will use this running example, x1 or x2 and x1 or x3 not, meaning not x3, right? Or x1 not or and x1 not or x2, and the last one x2 or x3. Right, so this is an example, and let me remind you. So the bar means negation, right? So if x1 is true and x3 is false, then we have true or true, because negation of x3 is also true. Well, so we have some formula like this. Let's create a polynomial time algorithm which will decide if it's satisfiable. So we will create a graph. It will be a directed graph. Vertices are just variables and their negations. So in this case, we would have x1, not x1. I have this x1, not x1. X2, not x2. X3, not x3. Okay, this will be our variables, and then edges. There will be an edge from alpha to beta if there's a parenthesis or clause in phi which looks like not alpha or beta, or beta or not alpha. It's pretty much logically it's the same statement. So for example, there's a clause here, not x3 or x1, therefore there must be an arrow from x3 to x1. Okay, and what is the meaning of those arrows? This is logical implication. We are secretly saying if alpha is true, beta must be true. Why is that? Because this clause has to be true, this parenthesis, but not alpha is false because alpha is true. Therefore, beta be true. Beta be true. So this just it's a logical implication. If we have a satisfying assignment in which alpha is true, and this is one of the parentheses in our formula, then beta also has to be true. That's it. That's what it means. So let's see what this graph is in this case, for example. So one thing to observe is that arrows come in pairs. For example, the same one could be interpreted as when alpha is x1 bar and beta is x3 bar. Right? So it means that because alpha bar would be x1 and beta would be x3 bar. Right? So you could interpret the same parenthesis as alpha bar beta for those alpha and beta, and that this means that there is error this way. This way. This is this way. And of course, this only makes sense because alpha implies if alpha then beta is equivalent to saying if not beta then not alpha. Okay, so arrows will come in pairs like this. Let's see what other arrows are here. So there's four parentheses, so there should be more such arrows. So this one, x1 bar implies x2, and such a thing, which immediately also gives us that x2 bar implies x1. We already did this one. Now this one tells us that x1 implies x2. And also it tells us that x2 bar implies x1 bar. Right, so x1 implies x2, x2 bar implies x1 bar. And the last one, x2 or x3, this means that x2 bar implies x3, and x3 bar implies x2. So we get the following graph, unless I made some mistake, out of this formula. Now we claim the following. We claim that phi is not satisfiable. Not satisfiable if and only if there is path from x to x bar and from x bar to x for some x. In other words, we need a pair of paths, right? So if there was like x, we go somewhere, then we go somewhere else in this graph, arrive to x bar, and then x bar goes somewhere, arrive to x. If there is basically such a cycle, then phi is not satisfiable. In one direction is pretty clear. Well, first of all, let's say this is true. Why does it mean that there's polynomial time algorithm? Well, we've seen before this kind of problem. We started with this. So it reduces to graph connectivity, right? So basically, you can just try to check for any x, which it's linear, input size or whatever. You can check is there a path from x to x bar in this graph, and this is done by brush it through the graph, adding more vertices to x. You keep adding vertices to which you can get from x until eventually you stop. And if you stopped and you exhausted the vertices to which you can get from x, and you got x bar in, then you're done. And if you didn't, then you didn't. So this way, for any x, you can check: is there such path? Is there such path? And then if there is an x where both exist, then you say no, it's not satisfiable. And if it doesn't, then you say yes, it is satisfied. Right, so this can be done in polynomial time. It's similar to the graph connectivity problem we started our first lecture on this topic. So the real question is, why is this claim true? Why is it true? And in fact, one of the two directions is easier than the other. So let's say there is a path from x to x bar and from x bar to x. Right? So there's, I think it's illustrated. So there is some path from x to x bar and from x bar to x. What does it mean? We said that those arrows mean logical implications, right? So in our satisfying assignment, imagine that there is one. If x was true, then x has to be either true or false. So if x was true, then this thing would be true, this thing would be true, all the way to x bar would be true, which is impossible. If x is false, true, then x bar is false. It's impossible for them to both to be true. Therefore, we would conclude that x cannot be true. Therefore, x is false, and therefore bar x is true, so this guy is true. But then we run into the same problem. If this guy is true, then this guy is true, then this guy is true, and that's impossible because bar x and x cannot be true at the same time. So basically, the reason why such satisfying assignment wouldn't exist is because if x was true, it would have to be false, and if it was false, it would have to be true. Therefore, basically, there's no x can be neither true nor false, which is of course impossible. It has to be either true or false. Okay, so the interesting part is the other direction. So let's say such thing doesn't happen, right? So this is clearly a problem if such thing happens. If there is a path from x to x bar, and there's path from x bar to x. But what it's not clear that that's the only problem. Like maybe there's some other reason why things could fail. Maybe that's not the only reason. So this claim says that it's not the case. This claim says that as long as this particular thing doesn't happen, where you can find x and x bar such that there's paths from one to the other and from the other to the one, then there is a satisfying assignment for phi. And we're going to prove it. We're going to prove it by kind of building it recursively. You're given an algorithm to build it. So let me just erase this part again. I'm just tiny board here. So let's see how we can prove it. So here's what we're going to do. Pick alpha such that there's no path from alpha to alpha bar. Right, and such alpha exists because if alpha doesn't work, then alpha bar does work, right? Because we're assuming there's no both paths from alpha to alpha bar and alpha bar to alpha. Therefore, even if there was a path from alpha to alpha bar, you just switch to alpha bar, and there is no path from alpha bar to alpha. So pick such an alpha, assign true to things reachable from alpha, meaning that you start with alpha and you follow arrows, everything alpha, this guy, this guy, this guy, all of them are assigned value true. And assign false to their negations. Right, so if alpha was assigned true, assign alpha bar false, etc. And then repeat, meaning that if you didn't assign everything yet, then pick a new thing which you didn't assign, pick one which has this property, and then assign again, and keep doing it until you assign everything. So why does this algorithm work? First of all, why does it not create contradictions? Okay, so uh, in fact, if it does not create contradictions, then uh, let's see. So I claim that then it's easy to see that each parenthesis will have at least one thing which is true, right? So why is that? Because assume, well, let me think about it. So why does this give us a satisfying assignment? Well, because by construction, uh, in each parenthesis, we assign of the one of the two values first, and whichever we assign, we would have assigned the other one correct value to make this parenthesis to be true. And therefore, neither of them could give us a contradiction. That's it. So the real problem is, well, it's not a problem, but the real question is, why does this algorithm actually run coherently? I mean, why does it give us coherent assignment of true and false at the end? Because you can create whatever algorithm exactly you want, but what if it assigns at the same time something to be true and false? Then we have a problem. Then we don't know which one it should be. So that's what we claim. We claim that it doesn't assign the same variable value true and false. So imagine that for some alpha we would reach some variable beta and we would assign value true, but we would also reach variable beta bar, and therefore we would assign beta value false and beta bar would be true. That would of course create a problem because it would mean that there is no satisfying assignment. But remember that our arrows come in pairs. If there's arrow from alpha to whatever gamma is here, it means that there is an arrow from uh, gamma bar to alpha bar, etc. So if there is this chain from alpha through gamma to beta, then there must be an opposite chain from beta bar to alpha bar. And similarly, if there is a chain from alpha to beta bar, there must be a chain from beta to alpha bar. But now we have a problem because this is a cycle we talked about. In this cycle, it's possible to get from alpha to alpha bar, but it's also possible to get from alpha bar. Let's see. What did I mean to say? So something is not right. So if we can get from here to here, uh, then there's a path from alpha bar to alpha bar from beta. That's correct. And from beta bar. Oh yes, let's start off with alpha. Let's start with beta. So for beta, there is a path from beta to alpha bar. No, I'm still thinking. Why is this a contradiction? So was supposed to be a contradiction. So if alpha implies beta, then beta bar implies alpha bar. If alpha implies beta bar, then beta implies alpha bar. Why is this a problem? Uh, being able to solve it is a problem. Okay, now I remember what it says problem. Because we chose alpha such that there is no path to from alpha to alpha bar. Right? So this could happen, but this means that just our choice of alpha was not correct, and we prevented it. We prevented it by saying at the beginning that pick alpha such that alpha doesn't imply alpha bar. And that's a contradiction because here we can get from alpha to beta or beta bar and get back to alpha bar, therefore alpha implies alpha bar. So that's what the contradiction is. Therefore, it's impossible for alpha to imply both beta and beta bar. In this way, however, let's be careful because remember we are running it in some kind of stages. So for example, maybe we started with some alpha 1, and then we created a bunch of assignments which are true, 1, and then there are negatives which include alpha 1 bar were false, and they kind of like this, so they were false, and then we start with a new alpha 2. And the question is, well, what would happen if we started assigning true values and we try to assign true value to something which was assigned a false value on the previous step, right? That would be also bad. But this doesn't happen for the same reason. If there was a path like this from here all the way to here, then there would be this reflected path, right? That each edge has a kind of mirror image, which would come from negation of this guy, which is in here, and would go through negation of this guy, etc., until it would reach alpha 2 bar. But if there was such a path, it would mean that on this previous step, we would have continued over here. We would have kept assigning true values until we assign true value to alpha 2 bar, and then alpha 2 would have gotten false value. But more importantly, alpha 2 would not have been sort of unassigned. It would have already been assigned. And since this didn't happen, we conclude that it's impossible for alpha 2 to imply, to follow the arrows and get to something which was supposed to be false, but now presumably it has to be true. Okay, so you can think of, so there's possibly one kind of more bad thing which can happen. You could think, I mean, you could ask, why doesn't it assign false value to something which was originally true, but it's kind of very similar. So either way, you consider such cases and you conclude that you never arrive to a contradiction. You conclude that you never arrive to a contradiction, means that if you follow this procedure, then you will indeed assign, well, let's put it this way. So either you will find x and x bar such that there's a path from x to x bar and from x bar to x, but if this doesn't happen, then you will follow this procedure and you will assign the variables, and this will indeed be a satisfying assignment. And it will work, it will be a well-defined assignment, there will be no internal logical contradictions in it, and it will satisfy this 2CNF formula. Okay, so this proves that deciding whether 2CNF has satisfying assignment is indeed just there's a fundamental time algorithm to do it. But 3CNF, as we saw, it's somehow magically it becomes much harder. I mean, it's an NP-complete problem. Okay, so let's talk about one more variation of CNF. So we just said that 2CNF, for example, doesn't work in terms of being NP-complete. It's not NP-complete, meaning that if you have a 2CNF formula, which looks like this, right? Then, and you're looking for assignment of true false to variables, which makes each parenthesis true, then you can decide it in polynomial time. But there is slightly more general question. Let's say instead of trying to make all of the parentheses true, you just choose a number k and you say, all I want to know is if I can make at least k of them true. Right? And then this turns out to be an NP-complete and a cute result. So let me write it down. So given a certain number of clauses or parentheses, in a 2CNF formula, if there is an assignment well, let's put it this way. We are asking, is there an assignment that makes at least k of those clauses true? Right? It's a question about a pair. It's not a question just about 2CNF phi. It's a question about a pair, phi and k. So our language, remember this language, when we say our language will consist of pairs 2CNF formula phi and the number k, such that there is a way to assign variables true or false in phi so that at least k of its clauses are true. And it turns out that deciding that is an NP-complete question. So this is called Max-2 set. I guess Max, because we are kind of asking, can you satisfy at least that many, or in other words, what is the maximum number you can satisfy bigger or smaller than this particular number? So this is called Max-2 set, this language. And it's more general than 2 set because, as we said, if you choose k to be just the total number of clauses in phi, then you're asking for all of them to be true, therefore you're basically asking to satisfy phi. But you are allowed to choose k to be not all of them, just some part of them, some smaller numbers than all of them. So, and theorem is that this guy is NP complete. Just a second, sorry. Because if you get to function, okay, so the theorem is that this is NP complete. Let's prove that. So, as usual, I recommend you just pause a little bit and try to think yourself how to prove it. It's a really nice exercise. In this particular case, without a hint, I think it's sort of hard to come up with a way to do it. So it's kind of tricky. It's not hard once you know what to do, but it's tricky to come up with a good idea. So first of all, it's easy to see that it's an in NP, right? There's always this kind of separate thing you need to say that why is it actually in NP? Well, if somebody can give you a hint, they can just tell you what assignment to take, and it's polynomial time to check that it works. I don't think it's clear. I think it's clear that you only need polynomial time to check if it works. So the question is, why is it NP hard? And for that, we need to reduce some known NP hard question to this question. So what we will do, we will actually again reduce 3 sets to this guy. Okay, so we're going to construct polynomial time reduction from 3 set. And here's a key observation. Let's imagine that our 3 set has one of the clauses which looks like this. Right, so 3 set will have 3 things in clause. So let's say we have, I mean, what we are doing, we are saying that let's take some 3 set formula, and we want to create out of it this kind of formula, 2CNF formula, and the number k, such that this thing it's possible to satisfy k of them if and only if this original thing was satisfied. Right? So we're reducing 3 set to this guy. Let's start with some chunk of 3CNF formula. Here's a really neat observation. Let's create out of it a whole bunch of new clauses. Right? Here's one, and if I write x strictly speaking, it's not a 2CNF formula, but I can write x or x. And this will be true if and only if x is true. So it's just shorter to write just x, and you know what I mean by that. So let's just say x, y, z, w, where w is just some new dummy variable. It's just we introduce a new dummy Boolean variable, which can be either 1 or 0, right? So just completely a special variable out of blue for this particular parenthesis, right? So this is a new variable. Let's take not x or not y. Let's take not y or not z. Let's take not z or not x. Let's take x or not w, y or not w, and z or not w. Okay, so it's a bizarre choice, but let's make this choice. So we created here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We created 10 clauses for a 2CNF, right? So those, each of them is length 2, including the ones which are length 1. I showed you how to make the actual length 2. Now, how many of those 10 are true depending on whether x, y, and z are true? And here's something very neat to check. So let's check it. First of all, it's symmetric in x, y, and z, right? W is kind of different from x, y, and z. But if you just swap x and y, then it will just swap those two. This one stays the same, those two swap, and those two swap. But overall, you have the same set of clauses. So I claim that if all x, y, z true, in other words, equal to 1, 7 of those parentheses are true. Let's check it. So what if x, y, and z are equal to 1? So, well, we don't know what is. Well, let's see what happens depending on w. So if x, y, and z are true, then 1, 2, 3 are true for sure. Not x or not y is false for sure. This one is false for sure. This one is false for sure. This one is true for sure. This one is true for sure. This one is true for sure. So we have 6 clauses which are for sure true, plus 1, which is just w by itself, which still could be true or false depending on what w is. So we can make it true. In other words, if you choose w to be true in this case, we will make 7 of those true. So maybe I should write here the following. We can make 7 true equal to 1. Now, if 2 of x, y, z are equal to 1, right? So let's say x is 1, y is 1, z is 0. Right, and as I said, it's symmetric, so it's enough to consider just this case. How many of those are true? True, true, false. We don't know. Not x is true, therefore this is true. This is false. Wait, this is what am I saying? This is false, right? So not x is false and not y is false, therefore this is false, but those two are true. So true, true, false, we don't know. False, true, true, because not z is true. So that's already 4. Now this guy, true. This guy, true. This guy, we don't know. So overall, we had 6 which were true, and then we had w and z or not w. And actually, in this case, it doesn't matter. If you make w true, then this will be true, this will be false. if we make W false, then this will be false, this will be true. So in this case, we don't even have a choice, but this always exactly 7 of them will be true, but I'll write can make 7 of those true. There's two more choices. If one of x, y, z is wrong, right? So let's say x equal 1, y equal 0, z equal 0. We have true, false, false. We don't know. True, true, true. So 4, true. This guy is true, 5. And those two we don't know. So, but if we make W be false and therefore not W be true, then those two will be true and we'll have overall 7 which are true. So again, we can make at least 7 of those to be wrong. But the last case, if all x, y, z are false, 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 we don't know, true, true, true. And now the best we can do, we have choice this guy or those three guys. We can do those, make those three guys true by making W false. We'll have true, 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 but this will still be only 6. So in this case, we can make at most 6 of those to be true. And this obviously gives us the following simple algorithm for how to reduce 3 sets to our max 2 set. So here's what we do. We start with 3CNF formula, which consists of things like x or y or z, and another one, and another one, etc. Now, each of those create 10 new clauses out of each of clauses of those, and put them all together into one big 2CNF formula. Right? Now, you could ask, what is W here? So create a separate W for each of those. So here we'll have some W1 over here. Here we'll have, W2, etc. So there will be a separate W for each parenthesis. Right? So if this had n clauses, this will have 10 times n clauses. Right? So the number of, so we create a 2CNF out of 3CNF. It has 10 n clauses. So if there are n here, then this will be 10n of those here. And we choose our number k to be 7n. Right? So in other words, for this particular 10n long 2CNF, we take number k equals 7n, and we ask, is it possible to make at least 7n of them true? And from what we just saw, it's very clear that, right, so in this case, the best we could do is 7, but we could do 7, and in this case, we couldn't do 7. So that we only can do 7, also, at least 7n to be true if each of those gives us 7 true ones, which means that each of them has to be satisfied. Right? So if there was a satisfying assignment for this max 2 set instance, right, for this formula and for this number k, then there would be a satisfying assignment for the original 3CNF formula. And the other way around. If there isn't, then there isn't. So all in all, it reduces our 3 set to max 2 set. Therefore, max 2 set is NP hard. Therefore, to get, because it's NP, you know it's NP complete. Okay, let's do one more. Let's do one more NP complete reduction. It will be useful, possibly for your homework. So we've seen this question before. So let's call this question vertex cover. Right, we talked about such things when we talked about Koenig's theorem. Remember that maximal set of independent edges was minimal vertex cover or something like that, but it was only true for bipartite graphs. So let's say now we have just a general graph, and recall that vertex cover of a graph is a subset of vertices such that every edge is adjacent to one of them, to at least one of them. Right, basically, we want to hit all the edges. Right? We have a graph. We want to choose some vertices so that each edge has one of its endpoints chosen. So such a set of vertices is called vertex cover. And then, what is vertex cover as a language? It's a collection of pairs G and K, where G is a graph and K is a number, such that G has vertex cover of size K. Okay, so obviously, if it has vertex cover of size K, then it has vertex cover of any larger size. So the question here really is K enough? Right? So is it enough is choosing K vertex is enough to create a vertex cover, or do you always need more than K? Right, so such pairs which, when K is enough for G, is in our language, and we are given an instance of G and K, we are deciding if it's in or out. That's what vertex cover language is. And the theorem is that vertex cover is NP complete. So the claim is that this is NP complete. It's easy to see that it's an NP group. Why is it an NP? What kind of hint you could get? So if somebody just tells you the correct cover to K, can you check in polynomial time that it actually covers all the edges? Yes, just go through the list of all edges, and for each of them, go through the list of vertices. I mean, vertices which are in our cover, and check if its endpoints are in this list. So all of this takes polynomial time. Therefore, it's an NP because it can be verified in polynomial time. So as usually, the hard part is to show that it's NP hard. Right? So we need to take some promo which is known to be NP hard and reduce to this level. And we will again just use 3CNF. We will reduce 3CNF. Well, let's call the language CSAT to our vertex cover. Right. What does it mean? It means that we want to start with a 3CNF formula, create out of it some pair of a graph and a number. And we want to say that this formula is satisfiable if and only if this graph has vertex cover of this size. Okay, and if we can do such thing, and if it's done in polynomial time, then we created a polynomial reduction from 3SAT to vertex cover. So here's how we're going to do it. As usual, we start with phi, which is some 3CNF formula. 3CNF formula, for example, phi something like this: x1 or x1 or x2, and x1 bar or x2 bar or x2 bar, and x1 bar or x2 or x2. So this is a very simple formula, but it's just to illustrate what we will do. So we will create a graph and a number of it. So how do we create a graph and a number? Each will give us triangle, and each xi will give us edge connecting xi to xi bar. Okay, so let's do an example of how this would work here. Okay, there are three clauses here. So we create three triangles and we label their vertices correspondingly. So this one will be x1, x1, x2. This one will be x1 bar, x1, x2 bar, x2 bar. And this one will be x1 bar, x2, x2. Okay. In addition, we create, for each variable, we create a separate edge. x1, x1 bar, x2, x2 bar. And furthermore, between those two parts, we connect vertices with the same label. We don't connect between triangles like that, but say this x1 over here has to be connected to this guy, and this guy has to be connected to this guy, and this guy to this guy, and then this one to here, and 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 this one to here. Okay? So that's our graph. So assume we had little m of those clauses, and we had, or maybe let me write it just here, m of those triangles, and let's say we have L of those variables. Right? So we need to choose number k. Remember, our language should consist of a graph and a number. And we asked, does this graph have a vertex cover of this size? So we will choose our number k to be m plus 2l. Okay, so now I claim the following. I claim that the original CCNF formula has a satisfying assignment if and only if this graph has a vertex cover of this size. Right, so overall number of vertices here is 3m plus 2l, and we are looking for this, right? No, it's the other way around. So let's see, I got 2m plus 1. So there's overall number of vertices is 3m plus 2l. And we are asking that there should be a vertex cover of size 2m plus l. Okay, so let's do one direction first. Let's say this formula has a satisfying assignment. Include in our vertex cover all variables which are true. Maybe this guy is true and this guy is true. I don't know. It actually wouldn't work that way, so let me see. So actually a satisfying assignment here would be x1 bar and x2. Right, so this will be a satisfying assignment. So include in our vertex cover one guy from each edge of those, which is true in this satisfying assignment. One of them is true, one is false. Include the one which is true. This will give us this L. Right, there's L such edges. In each of them, we picked one vertex that gives us L vertices. Now, inside triangles, include in our vertex cover two guys such that the third guy is true. Right? So, for example, this guy x1 here is true, so I will include the other two guys. And for example, here, let's see who's true. X1 bar is true, so I will actually here I don't have a choice. I must include those two guys. And here, say this x2 is true, so I will include those two guys. Right. So you see, sometimes I have a choice because there's more than one truth in there, but sometimes there's not. I claim that it's a legitimate vertex cover. Why is it a vertex cover? In each triangle we picked two vertices, therefore all those edges in triangles are covered. All those edges between xi and xi bar are covered. And furthermore, edges connecting them, the only way an edge could be not covered is if it connects the guy who was the third guy, the true guy. But if this was true guy, then let's see, oh, I did it incorrectly here. So here the true guy has to be x2. I should have circled the other two. Okay, so here those two have to get circled. Right, so the third guy is this x2, but because we chose it so that he's a true guy, right? We started with a satisfying sign, and we know that each parenthesis has somebody who's true, at least one. But because he's true, it means that over here he's connected to somebody who's already circled, right? Because between those two, we circled the one which is true. Right, so those edges are hit because we just covered those two vertices, and this edge is hit because this guy is true, and therefore it's covered by this one. Okay, so now the other way around. Let's say we have a satisfying assignment, a vertex cover of this size. Well, in order to cover all edges in each of triangles, you need to include at least two vertices of those triangles, right? Because otherwise one edge will be not covered inside the triangle. Similarly, in order to cover this edge connecting xi to xi bar, we need to cover, including the cover, at least one of its endpoints. Therefore, we have to have at least that many vertices in a vertex cover. And because we're assuming that there is such a vertex cover, then it must have get equality in each case. So we must have chosen exactly two in each triangle and exactly one for each edge. But then if you look at it, you will see that the ones we chosen for as the ones in each edge, they can be used as a satisfying sign, right? Like, just like let's make those to be true, and you will see that each triangle has to have at least one true vertex. And therefore it's a satisfying sign. Okay, so this was the reduction. In this case, see you guys next time. You should really be you should really be working now on the homework on NP completeness.